Okay, now I'm recording. Okay. All right, for people. Okay, I just turned on the recorder. Now this is for people who watch this later. We missed a little bit of the first part of the class, like just about 10 minutes or so, I think, not long. I'm just talking about how you build a simple recursive JavaScript max MSP JS object, and we'll go from there. Again, you haven't really missed much. I just talked about how you instantiate the JavaScript stuff and everything like this. If you have questions about it, send me some email and I'll answer it. Okay, anyhow, but we have this, and also I'm not doing very well at typing tonight. So they all have really weird names. That was supposed to say recurse, and that was supposed to say class fract, but yeah, I'll change it for the thing. All right, so we got this function bang post hey hey hey, and when we turn it off, let's send in a bang and see what happens. Okay. Okay. Again, I'm going pretty slow here, and I'll pick it up in a little bit. Okay. But if I say bang, look, hey, it says right over there, hey hey hey. So it's working. It's getting our bang. That's how we're going to set things off. Well, what is it we're going to set off, all right? Well, the thing we're going to set off, get rid of this now, is this recursion. And like I said, if you're going to recurse, you have to have a function to do it, okay? And I'm going to call this function, I'll just call it recurse. You can call it anything you want, okay? Okay, and I'm going to pass in a number. I'm going to call it cur level. Remember I said you have to keep track of how many recursions you're doing, because otherwise they'll go forever and, the universe will crash. We're going to use this to keep track of where we're going, okay? And here's what we're going to do. We're going to do something very, very, very simple here, okay? We're going to say post, here we are in level, and then I'm going to say cur level. Now, this is one of the fun things about JavaScript. See, look, I cannot type. It's just wrong. Okay? You can put in these strings here, and it'll print them out just like we did with the bang string. But then if you leave a space and you say plus and then a value, a variable, it'll simply just put the value in. So we should see the values of this. Well, what is it we're going to see? Well, we're going to see this, okay? We're going to say if cur level is greater than something, okay? We don't know what that thing is yet, okay? Then what we're going to do is return, because that's where we're going to stop, okay? Otherwise, I don't really need to put in an else here, because it's just going to fall through there. We can say cur level equals cur level plus 1. Now, there's also, you'll see this in some of my code, there's a very clever way to that cur level equals cur level plus 1. You can simply say cur level plus plus. Okay, that's like a magic, it's called a pre and postfix operators, and it will add 1. It's such a common thing to do that you don't always want to type out cur level equals cur level plus 1. You can just say cur level plus plus, all right? And we're then going to do this. We're going to say recurse cur level. Yeah. All right. Now, this is all ready to go, okay? Recurse, we're going to call this from bang, okay? And then we're going to call itself again after it adds 1 to this cur level, okay? So that's how we keep track. But we need to know, where are we and how do we know when to stop? We're going to decrease a variable up here. We're going to call it var n levels. I actually did type it right there. And in our bang function, we're going to set it. We're going to say n levels equals, let's do 7 levels, okay? And once I set that, then I can call recurse. And we're going to start at level 0. All right? So here's what happens. This guy, I declared it out here because I want it to be able to be used in the bang function and in the recurse function. So if you define a variable outside any function, it's available in any of those functions. If I define the variables just inside a function, then it's only available inside that function. Just a thing to know, okay? So it's going to set the number of levels to 7, and then it's going to call recurse. Recurse is going to take that, and the cur level is going to be 0, okay? then it will print that. And if cur level is greater than n levels, then it returns. We're done. Otherwise, it's going to add 1 to that 0, so it'll be 1, call recurse again, go through the whole thing again. Now we're in level 1. Is it greater than 7? No. So then it adds 1 to it, calls it again. So that's the recursion. Okay, very simple. Okay, so let's see how this works when we play it. Okay, so watch over here. And you'll see the amazing magic of recursion. Whoa. Ah. You'll see the amazing magic of recursion with the unamazing magic of Max MSP's sort of weird formatting. Okay, so it did it, but it put it all on one line. Okay, and there's not a real good way to, yeah. What we need to do is add, this is going to look weird, a new line at the end of it. Okay, so it's going to say, here we are in level blank. It will then put in the variable, and then in this version, it didn't do anything else. This says put in. That's a symbol for a new line. Okay, that's just some basic nonsense that you'll have to do. Okay, so now when I do it, yeah, now it looks like that. So it goes all the way down to level 8. Then it says, oh, I'm greater than level, so I return. Then I return. Then I return. Then I return. Then I get all the way back up. And life is good. That's the essence of recursion. Okay. All right. So what do I want to do? All right.
Mark, can I ask?
Sure, by all means, please.
It's actually on my Mac. It actually prints out the results when I save the recurse function. But when I like click the button, it didn't really return anything.
Let me see.
Okay. I mean.
You got the first recurse in the.
I mean, right now it's not printing anything. If I save it, it'll print the whole thing. But if I close it and click this,
Yeah, that's because the bottom is the band function.
it's a band function. It's not.
Right. That recurs inside the
Yes.
Right now, it's
okay.
just running. It ran because as soon as you put it in, this is outside anything. So it just goes, oh, I'll do recurse. I know.
Oh, okay.
You want to be able to trigger recurse or recurse.
Oh, got it. So if when I save, it just runs through the whole thing.
Then lock it again.
Thanks.
Hey, that's a feature I didn't even realize it had. That's kind of cool.
Yeah, that's interesting.
Okay. All right. So, sure.
Where do we save the recurse file again?
Okay. It does it by default. Okay. When I create a new Max JavaScript object, okay, it saves it in where you have saved your Max patch. Okay. So I had saved my Max patch inside that week 5 folder of mine. And then when you save, it'll save, by default, it'll save the JavaScript script in the same directory as the Max patch, which is what you want it to do. Yeah. Okay. Right. Yeah. Okay. All right. Let's make this a little bit more interesting now. Okay. And let's how do I want to do this? Do I want to go through this? Yeah, maybe I do want to go through this. Okay. Yeah, that's not too bad. Okay, I'm going to save this now again. Okay, I'm going to save it as, put it in the same directory, and I'll call this one class frac2.maxpatch. Okay, and I'm going to create a new JavaScript file, and I'm going to call it recurse2.js. Okay. And it'll tell me, oh, you don't have a file there. That's because I have to close this, double click, save it. And it'll say, do you want to save it with that thing? Yes, I want to save it exactly right there. So now it's happy, okay? All right. So here's what we're going to do. This time we're going to add that divider thing. that I talked about. You know, that's going to, like, you know, take it and split it up. Okay. So let's create here. Let's go in and just go ahead and build this. This will be the last one I build, I think. We'll say function bang. So this is what's going to start it off. Okay. And we know we're going to call recurse eventually. Okay. Only this time, we're going to call recurse, and we're going to give it a span, 0.0 to 1.0, and we're going to give it our cur level. Okay? Okay, sorry, I know you're following along. I'm kind of typing this sort of randomly because I want to fill it out a little bit differently. Okay, now we also know that we need to have a global variables that we call var n levels. Okay, and we're going to say n levels equals 7. We'll do 7 levels for recursion, okay? And we'll say our cur level is 0, okay? Then we're going to have one more thing. We'll make it global just so we can access. We're going to have a thing called the divider. And we'll say divider equals, we'll make it simple. We'll make it be 0.5 at first because we can very easily see how that recursion is working, okay? So now, we've set up our bang function. It declares how many levels are going to recurse, sets our current level, it assigns a value to the divider, and then it calls recurse. And recurse has 3 parameters this time. So we've got to make this recurse function. Function recurse, okay? And we're going to say low, high, and cur level. Okay? And what we're going to do is we're going to say, first of all, if cur level is greater than n levels, then what do? We return. Yeah. Now, I'm doing something else here just for pedagogical purposes. Notice that I don't have any curly braces. If you have an if statement and you only have one statement after it, you don't have to use the curly braces, okay? Do you want me to use the curly braces anyhow? Yeah. Just to make sure everybody knows what's going on here, okay? Otherwise, here's what we're going to do. We're going to create a variable. We're going to say midpoint. We're going to declare a variable var midpoint equals, let's say, divider times high minus low plus low. All right. And you know what? I don't need those. I need that there. Okay. What are we doing here? No, that's not what I want. We don't need this at all. Actually, what am I doing here? This is where it goes. You don't have to have it, but it's more. All right. We're taking the high value, which will be 1.0 and 0.0, and we're going to multiply it by 0.5 to get our middle point, okay? And because we're now going to go down these different sides, we have to choose which section. So that's why we're adding the low to it to get to that point, okay? Let me do it without that, first of all, okay? Okay, let's just do it like this, okay? And see what happens, okay? And now, what we're going to do is we're going to call recurse again. Oh, we're going to print it out, okay? We're going to say post, okay? And we'll say cur level plus mid TT plus. And now we learned our lesson, we have to put in a /n at the end. Okay, what does that translate into? Okay, this is going to print the value of our current level, and then it's going to print a colon and a space. Then it's going to print the value that we calculated this midpoint. and then it's going to print a new line, so we don't get it all on one line, okay? So once we post it, since we're just interested in looking at this stuff here, we're going to say recurse, and we're going to say low and midpoint. So now our midpoint becomes the high value, because we're going to go and recurse down that stream, okay? And let's just do that for now and see where that gets us, okay? Save. Uh-oh, I got a syntax error.
I think mid PT isn't safe. At least that is what it says.
What does it say?
That mid PT is not defined.
It says it can. Mid PT. It should be defined. It's right there.
Three variables.
Oh, it does. Yeah. That's the problem. Okay. Nico, I'm not sure what's going on with yours. I'll have to look at it. Okay. Oh, and I forgot to, this would have been bad. I forgot to add 1 to cur level, too. Cur level. Otherwise, it would recurse forever. And I'll just say equals cur level plus 1. Okay. What the heck is going on here? Okay. There. Life is good. Let's close this off. And now, watch what happens. Here we go. I'm going to clear this out. Hit bang. Boom. Whoa, what happened there? Okay. Boom. All right, that's what, somehow Zoom did something weird, okay? And you can see it did it, okay? Start out, first level, the midpoint was 0.5. The second level is 0.25. Third level is 0.125. So you can see it's going down, and it's like basically going down this one side, okay? We wanted to go down both sides. How do we do that? Well, let's go back here, and what we're going to do is we're going between low and midpoint. We want to go between midpoint and high. And in order to accomplish that, we have to add the low part. And we're going to add a second recursive between midpoint, which is now our low. That's why we have the hat over here. And our high. There. That's all we have to do. Okay? Because now this will go down, each time it divides it, it will go down both sides of the divider. Okay? So watch what happens now when we hit this. Oh, we get a whole lot more numbers. Yeah, look at all that, okay? In fact, let's make not so many levels so that we can like make more sense of it. Let's just make it do like 2 of this, okay? All right, and then we hit this. Let me clear this out. Hit this, bang. And now you can see, goes down this one side, 0.5, 0.25, 0.125, 0.375, 0.75, 0.625, 0.875. So it's actually doing the kind of thing we wanted. Of course, actually going down on all the different sort of recursion dividers that we need. So that's the essence of fractals, okay? All right, and the fun thing to do, of course, is you don't have to use 0.5 because that's going to be kind of boring. We can use 0.78 if we want, okay? And then we'll get something like this, okay? With all kinds of interesting sort of values. So it's spaced in kind of interesting ways, all right?
Can you show the bottom of the JavaScript object again?
Sure. There's the whole thing. All right. So basically, we've done the recursion part. Now we have to think about plotting it and solidifying it, okay? There's a problem here that I discovered, and yeah. Shut this out, okay? Notice that when I hit bang, it gave us like all the values at once, all right? that's a problem because we want to send those values to our plotter and to our RTCMix script, okay? The problem is that in a given sort of section of time, like remember, let's talk about plotting at first. Remember that the windows in processing only get updated about 60 times a second, okay? If you dump a whole bunch of data on it within 1/60th of a second, which is what this would do, it will only look at the very last thing you sent, and you won't get this nice plot, okay? Same thing with RTCMix, only the timing is a little bit tighter for that, okay? So we want to send this stuff to RTCMix and to the plotter in a way that they'll understand it, okay? And the way to do that is to not send it as single values coming out, okay? But to send it as a list of values that it has calculated. RTCMix can then look at that list and go, okay, I'll schedule these notes here, 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 and here. And what I'll do is I'll schedule the plotting here, 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 and here too, okay? So this time I'm not going to type anymore. I'm just going to bring up what I've done already because it'll take me too long to do this, okay? And let me make sure, tract 3. I think this is the one that has that included. Let's double check here.
What you do if it says no function bang, and I check my code and it's
Okay.
fine.
Let me see. Okay, double click on your JavaScript. Function bang. Function bang.
Maybe you just save the backup.
You did.
You already.
Oh,
So-
I didn't save it. Because I still don't have it.
Computers are really annoying and stupid things, you know that. Yeah, the not saving of it. Yeah, that's fun. Okay. All right. This is the one we want to look at. Okay. And this is going to be a little bit messy. Let's see if I can. For some reason, it's not allowing me to click in there. There we go. There we go. Okay. Ah. Hey guys, for some reason, I think my computer is not being happy lately. Let me check something here. That's working. Sorry about that. Let's go back here. There we go. Whew. I'm just not clicking very well, okay? Okay. Now, I don't know why that always comes up. That's just annoying, okay? Now, where's my class fractal 3?
I think it was also closed when you closed the other
I think you're right.
one. That's really weird. Why?
I have to investigate. Something bizarre is going on here, okay? All right, there. That's what we wanted to see.
Maybe just minimize it.
Yeah, that's what I'm going to do. Okay. I did that for Dave Sulzer's class, you know. All right. All right. Now, here's the way. This is like, you know, I'm just going to kind of walk through this briefly, and then I'm going to like just put it up on the website so you guys can take a look at it. Okay. The meat of it is down here. Okay. What we're doing is we're storing in an array. I've declared an array up here, okay? And basically that means that we can take and add stuff to that array, okay? And we're adding the index and the index plus 1. We're adding the point of the sort of fractal divide, and we're adding 1 over the level as an amplitude. So we'll get like a nice amplitude shape too, all right? And then we just do our recursion again. We continue to add that to the array. So this array is now going to be filled. Instead of printing the data values out or sending them out to the max MSP, we're going to create this big array, all right? So in the bang function, that starts our recursion. It does all the stuff, and it's adding all this array stuff down here. Down here, okay? This is where it's like filling the array with the midpoints and the stuff like that, all right? Then, after it finishes the recursion, this is a special JavaScript feature which will take the array of numbers and put commas in between all of them, which is what we want in our RTC mix. And then we need to say text, and we give the array a name, and then we add this thing called the outstring, which has all the commas in it. And then we add a final curly brace. This forms an RTC mix expression. It will say, I have an array here. It's called time amp points. Here it is, all right? And then we say outlet 0, and we give it that string. That sends the whole thing out the outlet, and we'll see what happens. Where is my fractal 3? Oh, that's what it's called. Okay. So it comes out here. This is a little bit of weird maxness that you have to do in order to get it from that text thing to RTC mix. Sends it into RTC mix, and it sends it bang to trigger RTC mix. Well, what's RTC mix going to do? It's very simple. Okay? I'm basically going to go through that whole array that I constructed, incrementing by 2, because I have both the time value and the amplitude value. And I'm going to use this instrument called the M shakers, okay? And that's the start time of it, which I get from that array. That's the duration. The amplitude, which is 20,000 times the value I get from the array. And then the rest of this stuff is just like, you know, the things that are equivalent for this particular shaker thing. And I believe I have it said this is a physical model of a tambourine, okay? So what we should hear is the fractal thing should like do like little tambourine hits. And I set my time span. Since the fractal thing was predicated on 0 to 1, so it's all going to be like 0.5 and 0.9 and 0.732 or whatever. Okay, I'm just going to multiply that by the time span, which I do right here. So I'll get points between 0 and 5. So I'll have 5 seconds of fun tambourine stuff. And then here's the fun part. I send those values out with the max message. Remember I said that processing was kind of slow? Well, I send the message out, and then I give it the X val and the Y val, and I send it over my UDP thing, all right? And it gets sent into, I think it's this one. Just double check here. I'll start this up. This may not be the right one. Okay. Go processing go. Remind me not to quit processing when I turn this, because we're going to use it in the next one too. Okay. Come on, computer, you can do it. There we go. All right. Yeah. So this just takes the X val and the Y val, and all it does is plot it. Only this time I'm using a line, okay, not a point. And you'll see how that looks. And again, I'm not going to go into the details of how that works because I'll put this up on the website, and you can look at the documentation online. Basically, you give it the X value and the Y value of the upper corner, and then the X value, and then the Y value is the height of the lower corner, okay? So that's that. Let's start up our processing. Don't need this one. Here we go. And you'll see the magic now. When I hit this, and I hit this, you'll see the fractal points start to get plotted down here when you hear them being hit, okay? Turn this up a little bit. Okay. It wasn't very loud. And you know what? It also occurs to me that I don't have this set to go out to Zoom. Hang on a minute. Yeah, hold on. Options. Audio status. Okay. Zoom. Oh, it is going out on Zoom. Okay.
I think that's why it is so quiet.
Yeah, it could be. All right.
Yeah.
Turn it up over here. Right. You know what? Again, for pedagogical reasons, I don't want to mess up the code too much. So I haven't implemented a clear function for this. So all we have to do is restart it. Okay. Here, we'll put this guy over here so we can watch it. And here we go. Right. Okay. So what's fun is that this is actually correlated, and you're watching the plot happen when the sound happens too, which is kind of nice. Okay. Just for fun, let's go in and let's make a bunch more levels. So 3, let's make it do, say, 7 levels. Okay. Save. Okay. And now I won't bother to clear this out. You'll see the levels coming in. Here they come. Okay. Boy, that seems awfully soft. I hope you guys on the Zoom can hear it. Okay, but this is where it gets kind of cool, you know. Let's start this again. Okay. So now we got our cool fractal tambourine player. Okay. Yeah. And if we wanted it to be something maybe more beat-oriented, we can go in here to our RTC mix, get a time span of 10, and hear what that sounds like. Okay. Here comes our fractally thing. Go here, and here we go. Which is kind of fun, okay? It sounds very fractal.
Great beat.
Yes, yeah, you can dance to it. Okay, so that was that. Now, how are we doing on time? We're not doing too badly. Let me shut this all off. I want to show you now this other attractor.
Sorry, what is mapped to the length of it?
What's what?
What is mapped to the length of the?
Oh, that was just, we're generating relatively abstract fractal time points. They're all between 0 and 1, okay? Let me bring up the max patch again.
The level.
It's the
The
level.
tallest one is level 0. But that's
Yes, yes,
level
yeah.
1.
Oh, okay.
Right. I put in a secondary thing where basically 1 over the level was the amplitude. So as you get further down, the amplitude went from like 1 to 1/2 to 1/3 to 1/4, 1/5, like that. Okay. Sorry, I misunderstood the question. Okay. Yeah, I just thought, you know, it's okay to like hear it all at the same level, but it's kind of like boring. Like this. This had like a little bit more because it has to. Plus, it looks a lot more fractal, you know, and that's always important. Make it look fractal.
That level to pitch to.
Yes. Yeah. There's no. Well, actually, that's what I want to do. That's why I'm wondering if I'm going to play. This is actually a piece done by one of the luminaries of early computer music, a guy named Charles Dodge. He worked at Brooklyn College for years, and then found out that they were embezzling money from his account.
Oh.
It's actually true. Yeah, it's true. Like he was missing like $1 million, you know.
Whoa.
And so he decamped very abruptly and went to teach at Dartmouth for a while. He's retired now. But he got his original training here at Columbia, because we're great, go Lions. But one of the things he did was he wrote this piece. I wanted to show you a use of sonification that didn't rely on pitch. And fractals seem kind of interesting to me because you can interpret it as time points. But typically people who've done fractal pieces have interpreted these levels as pitch levels. And he wrote this piece called Profiles. I'm just going to play the first couple minutes of it. It's actually a very lovely piece, okay? So here we go. Okay. it's got like that kind of fractal shape to it, as it kind of bubbles up, it's obviously going up some kind of like one of the top level recursions and coming back down. But the whole piece is basically just one recursion. And he just set it up to kind of like.
How did you save the AIF file? The top one?
The what?
The AIF file, the
Yeah.
first one?
Uh-huh.
How did you save that? Where did that come from?
Oh, I had a copy of this piece. Yeah, yeah, from years and years ago. I'll link this in. It'll be on the webpage, okay? So you can play it or download it. It's in public domain, so life is good. Okay, yeah, I'm doing time, pretty good. All right, now I'm going to do one more attractor, and this one I'm not going to go through the code very much. I just kind of want to show you the attractor because there's an issue with this that's kind of intriguing when you start thinking about sonification. And then we'll look at some Lindenmayer Systems stuff, which is just going to be show and tell. So, we're done with the heavy stuff. But I will put up all the patches so that you can kind of go through them and see what you're doing. Okay, now, I mentioned you, how did I get that there? That came up with a date thing, okay? There's this great website called paulbork.net, okay? And this has been in existence for at least 20 years, okay? And I showed this to you last time. But basically, he's got all these things, and you can look at it. I'm going to look at the chaos sort of stuff. And he talks about it here. And then you see all these different chaotic things, okay? But the amazing thing is if you click on one of them, he shows you a plot. He's a computer graphics guy, okay? Oh, I chose the wrong one. Nearly all of them, if you click on it, it has the equations to make it work. And then he gives you the values. This is even more important than equations sometimes. The values that you need to use for the coefficients of the equation, okay? And I want to look at one particular one. Oh, Lordy. I clicked too many times. Oh, good God. Okay, Paul Burke. Yeah, there we go, fractal scale substance. All right. I want to look at this one, the Henon map, okay? First of all, because the equations are very simple for it. It's kind of remarkable. Actually, I want to follow up on a comment that you asked like several classes ago. What makes these things? Talk about that just before we leave the strange attractors. So it's the next x is 1 plus the previous y minus a, which he gives you down there, times the previous x squared. The next y is b times the previous x. That's all there is to it. And you can see it's kind of weirdly tangled, so it's kind of interesting that you've got kind of this weird kind of iteration thing happening like that, okay? And that's the kind of chaotic attractor that produces, kind of cool. Let's see what it sounds like, all right? So let's go over here. And the first thing I'm going to do, rather than starting with the sound, I'm going to start with a plot of it, okay? So let me go down here, and I'll bring up my Henon 1.maxpat. Okay, and basically there you can see I'm initializing all these values, sending them into RTCMix. Here's the equation for the Henon that I calculate. Then I switch the x's so that the x olds are the x news. Then I map them, and I discovered again by looking what the range of the outputs are going to be. I map them to a square. It's going to be 200 by 200. There's a reason for that, okay? I'm going to send a message out. I'm not doing any sonification. The message will go out here, unpack itself, and go to xval and yval of the Henon 1 plotter. Which again, we've already even seen this one. This is just like takes the xval, takes the yval, and draws a point there. Okay? So we're going to plot this Henon thing out. All right? Let's turn on our processing. Let's go up here. Let's turn on RTCMix, and I'm going to start it out. And it's got a max bang coming out every 10th of a second, I think. And watch down here what happens, okay? Boom. Oh, wait. I forgot to initialize my values. Click. And then. So you can see, as you calculate the thing, it's filling out that attractor. And that's what's weird about it, is that it doesn't do it like the population equation where you're moving a single value. It doesn't do it like the Lorentz attractor where it's moving the stuff around. It's kind of doing it weirdly randomly, but all the points are falling along that attractor. That's why it's called a strange attractor. That's why it's called an attractor, actually. However, this presents a problem for us if we want to sonify that, okay? Because if we'd simply just sonify the pitch of it, like if we take the x or the y-axis to be the pitch, you know, it's just going to sound like random sounds because they're coming all over. And you can't really hear that attractor. And what we want to do is hear that attractor, okay? So what's an alternative way to approach this? Well, the scheme that I came up with is to plot a point and then start a process that will scan along this. And if it encounters a point, it will then send a note. So we'll hear the attractor as it's being built by this scanning process, okay? And let me bring up, it gets a little bit weird. Let me bring up now the next Henon plotter. Okay. 2, is this the one? Let me see. Yes, okay. All right, let's get rid of Henon 1. Okay, and I think I need to bring up now Henon 2.maxmap. Get rid of Henon 1. Okay. Yeah, now I have another one here. Scanner is being set to 0. And everything, if scanner is in fact 0, it does all the stuff to calculate and plot the points. Sends out to the points, but it's also sending a third thing, this scanner, okay? I'm going to add 1 to the scanner each time, and when it gets greater than 200, remember I said the thing was 200 along the x-axis? When it gets greater than 200, it'll set it back to 0, okay? So these points are going to then be plotted, and this scanner, what are we going to do in processing to show what the scanner does? Well, here's what the scanner does, okay? Okay. It's going to draw a point. And this time, I'm taking a little bit more interest in the color of things. And in fact, I set the background, instead of just using the default, I set the background to white, okay? 255, 255, that's the red, green, and blue values. And those are 8-bit quantities if you really want to know. That'll set it to white. And I plot the point, and I put red all the way up, and then blue and green as 0. So we'll get a red point plotted, all right? Then I'm going to set it to white, and I'm going to write another point that's one behind the scanner. Why am I doing this? Well, I'm going to animate the point along the bottom. And the way you animate something is you plot it, then the next time you plot it, you move it, and you draw with white over the previous one, and that erases it. So it creates the impression of this point kind of cruising along, okay? And I can show you that that actually works. Here comes our little thing here. Start this up. Finish like that, and now watch. See, there it goes. It plotted a point. Now it's scanning. Plotted another point. Now it's scanning along. Ooh, look at that. Plotted another point. Now it's scanning along. Isn't that cute? You can just watch that for hours. Okay. All right. Let's now add audio to this. Okay. All right. And let me think. I want to also bring up something else here. Well, let's do this. Okay. Turn this guy off. That's here. Henon 2A. I believe this will have the audio. All right. Yes. No, it doesn't. What is it? What am I doing here?
Probably the next one.
Yeah, I should probably. I have these written down in here, but like I put the whole code in there, and now I can't find anything. Okay. Oh wait, I was looking at the wrong one. Yeah. Yes, this is it. Ah. All right. but that looks the same. Okay. Yeah, we haven't done anything different here. I'm going to have to go to Henon 3, I believe. Oh, I know what the difference between those two were. Yeah, yeah. How are you on time? Good. Okay, I'm going to go back and I want to bring those. I want to bring this one up again. Okay. Okay. Yeah, there it is. Now, I discovered something. Let me go back to this Henon2.max. Okay. And let me now restart. I'll just keep this going as it is. Okay. I discovered something. Notice that with this, I'm adding an RTC mix output every 100th of a second, right? 0.01, right? And notice that it was kind of slow, okay? There it goes. So like if I'm listening to this, it'll go clink, 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 clink. You know, it's going to be kind of slow. So I thought, hey, I'll speed it up a whole lot. So I went in here. I said, I'm going to make it be 1,000th of a second. It'll really zip through there now. So I happily went to here, turned this on, put this in. Look, it's still slow. What happened there? Well, it turns out that this is a problem with using max bang to trigger things because it runs at a particular rate inside max. I'm not going to go into the details. There is a different way, however. And that's what this Henon 2A shows you. Instead of generating max bangs, I'm going to use their metro object, which basically generates bangs for me, okay? And that's running as fast as max can do it, so you can get much faster with this, okay? And this is the number of milliseconds, so this is now running at 100th of a second, okay? All right? So now, I don't have to have another bang coming back around, so I just send the thing here, and I just directly unpack the scanner, the X valve, and the Y valve. And now let me go back and restart my processing thing here so we can see it from anew. All right. Start this back up. Bring this down here. Start this. Initialize it. Initialize it. Start this up. Okay, already it's going faster, right? So, hey, I'm going to really make it go fast. So let's make it go 9. Okay, and let's 8. Okay, so now it's going plenty fast, but look what's happening down here. This is not good, but unfortunately, it's not fixable, really. What's happening is, remember I said that processing only runs at 60 times a second? This is actually forcing the data over there much faster than that. So when it tries to erase the point that was directly behind it, it's already gone too far, and it's missed out on erasing that point. So that's why you're getting all those like cruddy little points down there, okay? So I thought, well, heck, I'm a computer programmer. I have a solution for that. And I'll show you my solution, which didn't quite work, okay? All right, it is this one here. And then I'll show you the final version, okay? Where I don't draw a point. What I do is I wait for the scanner to reach 200, okay? And then what I do is, instead of drawing a point behind it each time, I let it go ahead and scan across until it reaches the end. Then I draw a whole rectangle of white over where it had been. So you're going to see it like draw a blue line out to the end, and then it'll blitz it out, okay? And I thought, well, yeah, because I'm only doing that once. So, you know, that'll be really good because I'm only doing it once. And let's set this back at 10. All right. Turn this on. Turn on our thing here, which I guess did come on, but it's hiding away somewhere. Where did it go? There it is. Okay. So put that down there. And now initialize, run, and there it goes. See? Cute, huh? Great. So I'm thinking, wow, I'm a pretty happy Brad right now. So now I'm going to, like, you know, because I showed how great a programmer I was. Now I'm going to speed it up a whole lot. Okay, and you can see the little points are getting a little funky there. Okay. Uh-oh, what happened there? Well, it didn't fix it. Because you're still going to miss sometimes when it should have drawn the rectangle, like right there, but it didn't because it was in the middle of doing its window stuff and the data came in. Okay. Now, there is a way to completely fix this, but it's non-trivial, and I'm not going to even try and do it. Okay. You have to store the values. You create what's called an accumulator, and then you deal with that from the processing end at the speed of processing. Okay. But we're just going to pretend that this is good, and we're happy. You know, we meant it to be that way because it gives it a little bit more of interest, you know, in terms of watching. All right. So the final thing I want to do to this is add some sound, okay? And that's going to be actually even weirder, okay? I'm just going to walk through this. Basically, I'm creating a giant array. Remember I said that 200 pixels wide and 200 tall was kind of done for a reason? That's because I'm creating an array up here that is 200 times 200. So basically, I'm creating an array that contains a map of all the pixels in that thing. And if I got much larger than that, it would be like a gigantic array. Okay? In other words, there's probably much better ways to kind of sonify and view the Henon attractor than what we're doing here. You know, this is where Python probably comes in really handy, or something like that. So what happens is this is just kind of like with what we were doing in the fractal thing, where we create an array to store our values. We basically store our x and y values in this array whenever they get pointed. So the array starts out initialized to 0. And then if I generate a point at 0.7 and 0.5, it puts it in the array in addition to plotting it onto the screen. Then what I do is after I send those values out to be plotted, I go through the array at where I am at the scanner, and I look at all the x values. And if there's a non-zero number there, then I go, oh, that should make a sound. And in this case, I'm then getting the frequency. I store the value in that thing, and I just grab that value from the array, do the map between there and there, between 100, I think, why did I say 700? Oh, it's going to be between 100 hertz and 700 hertz. And I'm using this thing from RTCMix. It's a physical model of a marimba called a mobile bar because I thought it would be cool to hear the Henon attractor's marimba. Again, I don't want to like belabor the point here. Like I said, I'll put the code up there. If you're really interested in doing more of this and you want to understand more of it, we can make an individual appointment, okay? Let me initialize this. Let me go out here and find my processing stuff. Processing stuff, where are you? Processing stuff. Processing stuff. Where is it? I must have closed it, yeah. Here we go. Okay, here we go. All right, so start this up. Bring it down here. Initialize my values. You can initialize it more than once if you're not sure, okay? And I started out like kind of slow at 20, okay? So here we go. Yeah, there we go. Okay. Let me speed it up. Let me speed it up a little bit more. Speed it a little bit more. Well, you get the idea, okay? Okay, so it's kind of like Steve Wright from hell, you know? But, you know, that's a way that I was imagining, you know, of being able to hear the Henon attractor as it filled out. And it does give you some interesting information about, you know, where parts of it are getting filled versus other parts or something like that. You can kind of hear the low stuff come in very quickly. So things like that. Anyhow, that's that. Like I said, I'll put that all on the web page. You can take a look. Oh, I was going to show you one thing. Nicola asked early on, you know, what is it that makes these chaotic attractors, have their particular character? What makes them be weird? And I don't fully understand them, but I made a very simple max patch that demonstrates what I think is going on. And there's two things that have to happen. First of all, there has to be some kind of, actually three things. There's some kind of iteration, where you're generating the values and feeding it back in. But in addition to that iteration, there has to be some kind of nonlinearity that causes the iterated points to kind of do weird things. But a nonlinearity by itself isn't going to help you because it'll generally just go off into infinity or negative infinity. So there also has to be a way of clamping the values. And I wrote a simple thing, kind of with those in mind. Basically, I just take the value and I square it, okay? And I start with the value between 0.5 and 1. Now, you square that, you get 0.25. So if it's less than 0.5, you add 0.5 to it. So 0.25 plus 0.5 is 0.75. Square that. And eventually, because it's all less than 1, it'll always go down, okay? But the descent is what's interesting, and this is where it gets kind of weirdly chaotic, okay? I do have this kind of sonified with a simple kind of Karpov-Strong algorithm thing. And listen to it. So you can hear it's got this chaotic quality to it. Sometimes you'll even hear sort of patterns that will repeat over and over again, but they're always going to be slightly off because of that nonlinearity. And that's about as simple as I could find. Y equals x squared. Just map it into a particular range and keep it clamped in that range, and you wind up with chaos. Such is life. All right. Let's put away max. Let's put away our processing, and let's just kind of look at some stuff now, okay? Lindenmayer Systems. Last thing we're going to do with this stuff, and then we're going to look at some real data, all right? Let me go down here. Henon. Boy, I just put way too much stuff in here. Here we go. All right. What is a Lindenmayer system? Well, there's this botanist named Aristide Lindenmayer, and he was looking at the way plants grew and the way that plants would branch and stuff like that. First of all, have any of you guys heard of this stuff? Do you know what I'm talking about? L systems? Okay, good. Yeah, well. Yeah, look what, there's Ezra. Okay. Yeah.
Luke's dissertation is on.
In fact, we're going to look at some of Luke's dissertation, yeah. Basically, it's a way of kind of using a fractal approach to model growth and form, okay? And it's done by using these things called grammars, okay? And I think that, I'll write this up. Yeah. Well, I can show you, actually, okay? The grammar, basically, you have these symbols, like A and B. And you say in the grammar what happens to them when you encounter the symbol. Like, say, I encounter an A. The grammar will say, well, an A is going to turn into an AB. If I encounter a B, what's a B going to do? A B is going to turn into an A. So you think, well, what does that do? Well, if you start iterating it, you'll get like A, A, B, A, 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 B, A, B, A, B, A. And you get these very interesting kind of sort of strings, okay? Let me show you how it works, okay? All right. Oh my gosh.
Is it a Fibonacci?
Objects missing.
I got like, oh my, I don't know what happened. Hold on. Yeah. First of all, let me get rid of Dave's scale.
It's a kind of like natural growth.
Yes. Well, it basically, it's what you do with the, yeah, okay. It's what you do with the grammar that makes a difference, how you interpret it, okay? Let's get this guy going now. Ah, much better, okay. Okay, So it's exactly what I said. B is going to go to A, and A is going to go to B, all right? So let me start this out, okay? Oh, that's going to play the music. I don't want to play the music really, okay? So I'm going to say, all right, let's start with B. Well, B is going to go to A. So if I hit this, bang, it turns into an A. So then I say, well, what's this? Well, it's an A. An A is going to go to an AB. So I hit that. I get AB. Oh, what do I do now? Well, I got an A. That's going to go to an AB. And I got a B. That's going to go to an A. So I hit it again. I get ABA. So same. A goes to AB. B goes to A goes to AB. Abab. Okay? And you can do this over and over again. And you get some really interesting results, even from a very simple thing like that. It's not really repetitive, but it looks kind of weirdly repetitive. Now, what's important is not really what the string is. Well, I mean, pure mathematicians, they like, you know, there's whole conferences devoted to like these weird strings and stuff like that, abelian strings, and, you know, it has to do with crypto and all kinds of things like that. But you can interpret this, and one of the ways to interpret it is with what they call turtle graphics. This was made by this guy named Seymour Papert, who was like big on like training kids how to do stuff. And he uses F's, pluses, and minuses. And a large F means you draw something as you move. A small f means you don't draw it. A plus means you rotate. A minus means you rotate in the other direction. So these strings can be interpreted as instructions for a plotter to go around. And let me show you what some of that looks like. Okay. So Luke came up with a whole bunch of different sort of things, all right? And you can go here, and here is, you can see now he's using this sort of F minus and F plus thing. Let's just choose one at random. We'll choose that one, all right? And if I say start the LCD, then I can hit a key on my keyboard, and it's going to generate what that initial axiom they call that F plus F minus F would plot if it was interpreted as one of these things. Looks like that. Well, let's do it again. Looks like that. Well, let's do it again. What it's doing is it's doing the fractal thing where it's going back to each of these nodes, and like then, because one of the instructions in the grammar is that you can branch out, then you come back. Do it again. Do it again. Do it again. And you start getting pretty insane sort of forms, okay? Let's clear it off, and just for fun, let's look at some plant life, which is what Lindenmayer is doing. Okay, and you see, it's not that complicated. If I click on that, then I generate it. It looks kind of like a plant. And what he's doing is he's imagining all the branchings and trees, that's being modeled by this Lindenmayer system, okay? So it's pretty intense, you know, and you can do a lot with it. The thing to really do, if you get really into this, is look at Luc Dubois' dissertation. This was his dissertation topic. And it's one of the best doctoral theses that I've read. It's very, very kind of readable, and it really covers a lot. Let me see if I can find it for you. And I'm going to show you, there's a piece that he did with it, okay? lucdubois.com. Let's go here. Okay. Let's go to projects 1994. Okay. And down in here, dissertation. Okay. Application of generative string substitution. Okay. And you can actually download the whole paper here. Okay. And like I said, if you really want to get into this stuff, I highly recommend it. And this is one of the pieces. He did a number of pieces with it. And this is one of the ones that he wrote for a guitar. This is a synthetic realization, so the guitar is going to be very mechanical sounding, but you're going to get an idea of what it to get to a place like this. And it's filled up quite well. You need to hear. So it's a very powerful and elegant tool for creating these sorts of compositions. I want to play another example. This is from another former graduate student here, Akira Takaoka. He's teaching in Japan now, and he also became very enamored of L systems and some other things using a thing called a Poisson distribution. But he did this work that's just gorgeous. Okay, Akira, yes, vanishing trajectories. Where is it? I thought I saw it. Hold on. Akira. There you go. Right. Okay. So what Akira did was he teamed up with a laser artist that's fairly well known in Japan called Keiichi Tanaka, and they did these collaborations where the laser artists used this L systems work to create these laser images, and Akira used an L system to produce the music, and you wind up with music like this. Okay, again, I'm going to run it forward quite a bit, you know. Still run it forward a bit. Just a recording of stuff in it. Okay, but basically, you know, really beautiful kind of evolving forms, you know, based on this sort of this whole L system stuff. You know, some of it looks even like Northern Lights, which
L system is Lindenmayer.
Lindenmayer, right? It's named after the guy, Aristide Linden, and they got tired of saying his name, so they just call him L system. Okay. Now, there's other things that you can look at. There's actually, like I said, this is kind of a big area of work. And let me see if I can find this particular thing. Yeah. So, yes. Okay, so this is kind of fun. You can actually go over here and look at some examples, and it will render it. And then you can go in and you can change things. Like, what if I change the angle if the turtle graphics is going from 25 to, say, well, it does that. Okay. What if I change it to 5? Well, it does that. You know? What if I change it to 178? Well, it does that. So this is kind of fun, and you can actually go in and modify the rules on these, okay, and try different things like that. You know? And I found a couple of other sites that do this sort of thing. This one's kind of cute because it animates the construction of it. Hard, what's that called? Hard. Software.com/projects. There we go. Okay. Okay, so basically, I can start with, do you want to start with a tree or do you want to start with a dragon curve? Okay, dragon curve, okay, all right. And there it tells you, like, what these different symbols mean, you know, and then it, I think, where's it saying where these are? Oh, here it is. These are the rules. Very simple, very simple. That's what happens, okay. That's the dragon curve, okay. And we can actually go further down. Let's do like maybe 12 generations. Okay. So these are kind of fun to play with, you know. And like I said, several of our students have found them very inspiring, including Dubois and Akira Takaoka, for example. I should say that both of these guys in computer music are really well-known people. Luke actually wrote the graphics that Max MSP uses called. Yeah,
Sir,
he did
is Luke the professor from Morrow?
yes,
Oh,
he was here. I've known Luke since he was 19 years old. Because he showed up here as a sophomore, and then went straight to his doctorate. And Kira is quite well known in Japan. He's the reason I've gone over to Japan quite a bit. It's fun, and I speak very bad Japanese. So, anyhow. I thought you might get a kick out of some of that stuff. Like I said, I'll put these links on the website, and you can take a look at it. I don't have any examples because I thought we were just kind of exampled out at this point. You know, I will put up the code for the things I did do today, the fractal sort of stuff and the Henon stuff, and you can take a look at that. And yeah, so we're kind of done with these attractors. Next time we'll look at some real data, and you know, all the stuff that we've learned here, you know, about applying sort of acoustic characteristics to particular values. Now we're just going to use them, but we're not going to have an equation that we're going to have to implement. We're just going to be reading data sets and see what we come up with. All right. That's it, gang. Okay, so everybody on the Zoom call, let me stop my file share. Okay, and I will stop the recording now. Bye.